Hello, my name is Dennehy, and today I'll be talking about portable water desalination. I think that it's important that everyone has an understanding of what scientists are doing right now in terms of water desalination, because it's ultimately something that's going to impact us all as time goes by. And additionally, it doesn't just impact us, it impacts animals, it impacts plants, and so I think it's crucial that we have an understanding of in the future where our fresh water is going to be coming from.
There are a variety of factors which help us recognize why we need to address the water crisis soon. Here's just some statistics. It's estimated that 2.8 billion people in 48 countries will experience water scarcity by 2025, and by 2050, 40% of the world's population will live in areas of water scarcity. Additionally, we need to reduce our reliance on fossil fuels such as oil and coal, things that will eventually run out and are bad for the environment. For power, we need to turn to things like there's a water desalination method that uses gravity, and the one that I'll be talking about uses sunlight, and we need to turn to those as those are unlimited and they are environmentally friendly. And finally, probably the most obvious reason that we would consider using saltwater desalination is that there's an abundance of salt water available. The widely accepted portable desalination methods using solar power are based on distillation. This scientific process is commonly used to separate two different substances. On the left, the Bunsen burner increases the temperature of the liquid inside the flask in hopes of evaporating the liquid. Each molecule inside the flask has a different boiling point, so the molecule with the lowest boiling point, in our case water, will evaporate first. This evaporated liquid will travel through the fractionating column, down the tube, and through a condenser, which uses cold water running through it to turn the steam back into liquid water. Finally, the liquid water will enter the flask on the right. It's important to note that it is possible for small amounts of dissolved particles inside of the flask on the left to start to evaporate, which in our case of salt water would be like sodium ions, chloride ions, magnesium ions, calcium ions, potassium ions, and they may evaporate, but it is highly unlikely because they have such high boiling points and are just solids dissolved in liquid. But the fractionating column ensures that they will not get into this flask on the right because it hopes that the solids will get stuck onto these grooves. This diagram shows how solar-powered water desalination would work in real life. Many of the ideas are similar to distillation, but some modifications were made to suit real-life conditions. For example, on the right, the system has a steady stream of seawater so that humans do not have to constantly attend to the system. Additionally, the Bunsen burner that was used in distillation to supply heat is now the sun supplying heat. Finally, there is the addition of this absorber/evaporator film, which acts like the fractionating column in that it ensures that no other molecules besides water are being collected here at the bottom. And additionally, this absorber/evaporator surface will try to maximize the amount of sunlight that is collected, but more on this later. There are several variables which can impact the efficiency of this system. For example, availability of sunlight. This system obviously would not perform well on a stormy or cloudy day because not much sunlight is getting into heating up the liquid. For temperature of surroundings and system, this process would not be efficient if it was snowing because it would be freezing outside, but also in terms of building it, making sure that the materials properly insulate the water that they're trying to evaporate so that it actually has a chance of evaporating. Scientists could come up with loads of factors which could impact the rate of desalination, so I just think that figuring out exactly how much fresh water produced would be the ultimate indicator of quite how efficient this system is. This picture on the right shows some of the optimizations that scientists have made. They want to maximize the amount of solar flux or sunlight entering the system, minimize the amount of heat lost by radiation and convection, and maximize the amount of evaporation that occurs. Additionally, if you'll notice, the absorber/evaporator surface is black. Scientists have already realized that if they make the surface black, because black absorbs all frequencies of light, it will have the greatest chance of transferring the most amount of heat to the water, and thus making the water the hottest it could possibly be. This absorber/evaporator system that I've been talking about is the main thing that scientists are currently focusing on. They want this surface to be able to maximize the amount of heat transferred to the water, as well as ensure that any dissolved particles are not escaping the inner chamber. And previously, they had been using gold nanoparticles to accomplish this, but obviously, gold nanoparticles are not going to be economically sustainable for this product. So, as of June 2020, which is actually quite recent, a nickel-infused aluminum surface was developed. To create this surface, first, the aluminum undergoes anodization, which increases the thickness of oxide layers that are naturally on aluminum. And by doing this, the aluminum now has these pores, which you can see in the second little picture, which the water vapor can escape from and sunlight can be absorbed by. Then nickel is deposited into these alumina pores to ensure that the surface becomes a selective absorber, meaning that it will only deal with selective molecules, and this system was scientifically calculated to have a 76.5% efficiency. Due to adhesion, which is water molecules sticking to other surfaces, and cohesion, which is water molecules sticking to other water molecules due to their polarity, this system contains a major flaw. When the water vapor evaporates, some of this water vapor will get stuck onto the Fresnel lens, which is up here at the top. Because of this, there are two new factors which limit the rate of freshwater desalination. This will reduce the amount of sunlight that is able to reach the inner chamber because these water droplets are reducing the sun's intensity as it wants to go into the inner chamber, in turn reducing the rate of evaporation and in turn reducing the rate of freshwater production. Additionally, this will reduce the rate of freshwater produced as some of the water will be stuck onto the surfaces of the system due to adhesion cohesion, specifically the top and the sides of the system. And so that freshwater will not be calculated into the freshwater calculation, and so it will not be considered as efficient. And then on the right here, this picture just shows what adhesion and cohesion forces look like on the sort of leaf. So it's the water molecules sticking to the leaf due to adhesion and the water molecules sticking together due to cohesion. When water vapor condenses back into a liquid, a large amount of energy is released. Scientists realized that they could recycle this released energy, or wasted energy as they like to call it, into generating electricity. Although it would be difficult to harvest a significant amount of energy from this heat in small communities, it could actually prove beneficial. And as of September 2020, scientists were able to generate electricity by harvesting this heat. To do this, they used bamboo. They recognized that bamboo is a great insulator of heat, and that is shown by the picture on the left. You can see that as the temperatures increase dramatically, which is kind of on the right, so the 67.8 degrees Celsius and 47.8 degrees Celsius, although the center of the bamboo is hot, noticed by the key on the right, so it's reaching 68 and 48 degrees Celsius respectively. The outsides of the bamboo are yellows, greens, and blues, which means that there's a temperature gradient between the center of the bamboo and the outsides of the bamboo. And by using this temperature gradient to their advantage, scientists were able to generate electricity. This idea is shown on the graph on the right. As the temperature gradient increases, the amount of volts produced increases as well. But note that a more negative voltage results in generating more electricity, as shown by the scale on the right of the graph, from 0 to negative 100 microvolts. The original water desalination model is definitely more advantageous than this bamboo model simply because it's scalable. For the most part, you can't really control how large a bamboo shoot is, but since this water desalination model is man-made, scientists can engineer it to fit any dimensions that they want. Overall, continuing research in this area will be crucial to all life forms because as time continues, the supply of fresh water is only going to decrease. Eventually, the system will have to be implemented in full scale and not just talked about in the lab. But there are many questions which will actually mold how this actually happens. I mean, obviously gold nanoparticles are not cost efficient and will be too expensive to implement this system. But will the nickel-infused aluminum surfaces be too expensive? Will these systems actually produce enough water that's needed? It was calculated that 50 units at 1 meter squared would be needed to produce enough water necessary for the average person in San Diego. It's not viable to have 50 units per person in small communities. So that's why further research is needed. Although these results are a step in the right direction, serious research continues to need to be done to ensure that in the future people will have access to clean water. Pictured here, I have the Carlsbad Desalination Plant, which produces 50 million gallons of water per day to people all throughout San Diego County. Although this is great, smaller communities do not have access to such grand of amenities. This is why research is needed to provide economically valuable systems to help people deal with the freshwater crisis.
I just wanted to thank you for listening to my project. It's something that I'm very passionate about, and it's something that I hope to learn more about, especially as I further my college career. And I also wanted to thank my mentor, Dr. Roberts, and I also hope that you learned something about water desalination, why it's so important that we continue doing research.